What if everything you've ever known, Earth, oceans, life itself, began not with a bang, but with dust? Around 4.6 billion years ago, before there was a sun warming our skies or a planet beneath our feet, there was only a cold, spinning disk of gas and microscopic particles drifting through space. From this quiet chaos, an entire solar system emerged. But how does lifeless dust organize itself into planets, atmospheres, and eventually living worlds? And more importantly, was this process inevitable or a cosmic accident? Scientists call this the protoplanetary disk model, a theory supported by observations from modern telescopes and by the chemical fingerprints locked inside ancient meteorites. These space rocks act like time capsules, preserving evidence of the earliest materials that formed the solar system. Radioactive dating shows that solids condensed rapidly, within just a few million years, suggesting that planet formation is not slow and random, but surprisingly efficient. Yet major questions remain. Why did Earth become a water-rich, life-supporting planet while Mars dried out and Venus turned hostile? Did the giant planets migrate, reshaping the inner solar system and determining our fate? And could the same process that built Earth be happening right now around distant stars, creating other worlds like ours? By tracing the journey from a swirling disk of dust to a living planet, we are not just studying astronomy, we are investigating our own origin story. This is a story written in physics, chemistry, and time itself. And as new missions and space telescopes push deeper into the universe, each discovery forces us to rethink a fundamental question: is Earth rare, or are we simply one of many outcomes in a universe that knows how to build worlds? Let's explore the evidence, let's question the assumptions, and let's follow the dust, back to the very beginning. Ever wondered where everything around you, Earth, trees, even you, came from? The answer: Stardust. Our story began over 4.6 billion years ago with a giant swirling cloud of gas and dust in space. This cloud held all the ingredients for our solar system, waiting for something to set the process in motion. Imagine before planets or the sun, just a cold, dark cloud floating in the void. The journey from that cloud to our world is a tale of gravity, heat, and time. Understanding this story connects us to the universe and reveals how rare and precious our planet is. Each step, from dust to oceans, was crucial for life to exist. By learning our cosmic origins, we see our place in the universe and the power of physics at work. This isn't just ancient history, it's the foundation for searching for other worlds and life beyond. The story is still unfolding and you're part of it. Let's dive in and discover how our cosmic neighborhood came to be. Our solar system began as a vast, cold cloud of gas and dust, a solar nebula. This nebula was mostly hydrogen and helium, with dust grains made from heavier elements forged in ancient stars. Picture a dark warehouse filled with floating specks. Now imagine that on a cosmic scale. For ages, the nebula drifted quietly, its particles far apart, waiting for a spark. That spark came from a disturbance, maybe a nearby supernova's shockwave. Suddenly, gravity took over, pulling particles together and starting a chain reaction. Gravity, the universe's master builder, began clumping the cloud's material. As more particles gathered, their gravity grew stronger, accelerating the collapse. This process set the stage for everything: the sun, the planets, and us. The nebula's dust, our future planet, was literally stardust from long-dead stars. We are connected to the cosmos in the most literal way. The solar nebula's collapse was the first step in building our solar system. From this simple cloud, a complex system would emerge. The story of our origins is written in every atom of our bodies. Let's see what happened next. Gravity pulled the nebula's center tighter, forming a dense, spinning clump. As it collapsed, the cloud spun faster, flattening into a disk, like a cosmic pizza. At the center, a hot, dense ball of gas formed, a protostar. The pressure and temperature soared as more material fell in. When the core reached millions of degrees, nuclear fusion ignited, hydrogen fused into helium, releasing energy and balancing gravity's crush. In that instant, our sun was born, lighting up the solar system for the first time. The sun's energy pushed back against gravity, stabilizing the newborn star. The surrounding disk, now bathed in sunlight, was ready for the next act. The birth of the sun was the spark that set planet formation in motion. Our star's ignition was the dawn of everything we know. Now, the leftovers in the disk would become worlds. With the sun shining, the leftover disk of gas and dust, called the protoplanetary disk, became the birthplace of planets. Close to the sun, only metals and rocks could survive the heat. Farther out, ices joined the mix. This difference explains why rocky planets formed near the sun and gas giants farther away. Planet formation began with tiny dust grains sticking together thanks to static electricity. Over time, these clumps grew into pebbles, then rocks, then boulders. As they grew, gravity took over, pulling in more material and sweeping their orbits clean. These growing bodies, called planetesimals, filled the disk, colliding, merging, and sometimes shattering. The protoplanetary disk became a chaotic racetrack of collisions and growth. Each impact was a step toward building full-sized planets. The process was slow but relentless. From dust bunnies to planetesimals, the building blocks of worlds were taking shape. The next phase, turning these planetesimals into planets. The era of planetesimals was violent, growth by collision. The biggest planetesimals, with the strongest gravity, gobbled up smaller ones, growing even larger. Each impact released energy, melting rock and forming molten worlds. Heavy metals sank to the center, creating dense cores. Lighter materials floated to the surface. This process, called differentiation, shaped Earth's structure. Hundreds of protoplanets orbited the sun, but only a few would survive. Giant impacts between these worlds determined the winners. Earth, in a stable orbit, grew by sweeping up debris and merging with rivals. After millions of years, only 4 rocky planets remained: Mercury, Venus, Earth, and Mars. The chaos settled, and the inner solar system took its familiar shape. The construction of planets was nearly complete, but Earth's story had one more dramatic twist. Earth's final transformation came from a colossal collision. A Mars-sized protoplanet, Theia, slammed into the young Earth. The impact melted both worlds and blasted debris into orbit. This debris formed a ring around Earth, which quickly coalesced into the Moon. The Moon began much closer to Earth, glowing from its fiery birth. This giant impact explains why the Moon's composition is so similar to Earth's mantle. The collision tilted Earth's axis, giving us seasons, and sped up our rotation. Over time, the Moon's gravity stabilized Earth's tilt and slowed our days. The Earth-Moon system is unique and vital for life as we know it. Our Moon's violent origin shaped the world we live on. Earth is special because it's in the habitable zone, the perfect distance from the sun for liquid water. Our size gives us enough gravity to hold a life-supporting atmosphere. This atmosphere shields us from radiation, burns up meteors, and keeps temperatures stable. Earth's molten core generates a magnetic field, protecting us from solar wind. Plate tectonics recycle nutrients and regulate climate, keeping our planet dynamic. The Moon's gravity stabilizes Earth's tilt, preventing wild climate swings. Tides from the Moon may have helped life begin in coastal zones. All these factors, location, size, magnetic field, and Moon, make Earth uniquely suited for life. Our planet is a rare oasis in a vast universe. The right conditions came together to make Earth home. The early solar system was wild. Giant planets like Jupiter migrated, scattering debris everywhere. Jupiter's journey may have robbed Mars of material, making it smaller than Earth and Venus. Earth's water likely arrived via icy comets and asteroids during the late heavy bombardment. The young sun was dimmer, but Earth's thick, greenhouse-rich atmosphere kept it warm. Mercury may have lost much of its crust in a giant impact, leaving a dense, iron core. Venus might have had oceans, but a runaway greenhouse effect boiled them away. The solar system's history is full of dramatic changes and cosmic close calls. Every planet has a story shaped by collisions and chaos. Our calm solar system today hides a wild past. The universe is a cosmic construction zone, always changing. Our journey through time reveals how stars, planets, and life are connected. Understanding our solar system's birth shows us our place in the universe. We're made of stardust, shaped by cosmic events and chance. Studying planet formation helps us search for life on exoplanets. Knowing what makes Earth special guides our search for other habitable worlds. Our planet's stability is the result of countless lucky breaks. This knowledge inspires us to protect our rare, beautiful home. Science is a never-ending quest for answers. Each discovery leads to new questions. By looking back, we light the way for future exploration and understanding. So keep asking questions and never stop exploring the universe.